Hello and welcome to this video workshop all about pHs and pKas. I'm Dr. Tom Robshaw. Before you start, advanced warning, you will definitely need a calculator or some way of computing answers like Microsoft Excel or similar to do some of the practice exercises from this workshop. This series of video workshops is designed to help the transition of foundation year and first year students into chemistry focused modules. People who maybe don't have a strong previous background in chemistry. This is one of our longer video workshops. You'll need up to 30 minutes to complete it properly. There are a number of quick practice questions throughout. At these points you should pause the workshop and go through the questions at your own pace. At the end of the workshop there are some additional slightly tougher questions to challenge you. You can download these via the link underneath the relevant video. To get the most out of the session you'll need a periodic table and something to write or draw with. Again, you can download the periodic table from the relevant SharePoint page. So here's what we're going to look at within this video. You'll learn how to describe the relationship between pH and concentration of protons, and similarly the relationship between the parameters pKa and Ka. We'll look at titration curves. I'll explain what they are and you'll learn how to interpret them. You'll learn how to recognize acidic and basic functional groups, and you'll be able to, following the learning material, you'll be able to define what the ionization and protonation states are of a drug molecule when you're given certain variables, specifically the pKa of the molecule in particular and the pH of the surrounding solution. Finally, you'll get a handle on understanding the behavior of buffer solutions and how they react to the presence of strong acids and strong bases. So, pHs and pKas. You've almost certainly heard of the first term, maybe not the second yet. Even though most people have heard of the term pH, not that many have a proper understanding of what it means. But first of all, why are these two terms important? Well, they're both absolutely fundamental to the working of the human body, for one. So there's a reason why the pH of the human body has to be maintained at 7.4 by homeostasis. If it isn't, we die. Simple as that. It's also very important with respect to the behavior of drugs as they enter the body. It's also extremely important environmentally. Okay, if we change the pH of a watercourse like a river substantially by polluting it, all the fish die because they can't tolerate the change to pH of their surroundings. It's also really important in a number of important chemical reactions. If the pH of the solvent isn't controlled, very often the reaction doesn't work. This is why you probably had a go at some point at measuring the pH of a solution in your previous education at school or college. Let's make sure we're clear on what these terms actually mean, and we'll start with the simpler of the two. So pH is a measure of the acidity or the alkalinity of a solution. Immediately having said that, we have to stop and take a step back, because what I'm doing here is introducing more terms here that we might not be completely familiar with. So let's go right back to the behavior of water. So in a glass of pure water, the huge majority of the molecules present will be H2O, oxygen in the middle, hydrogen on each side, and almost certainly you knew this already. But water has this rare property of being able to act simultaneously as an acid and a base. And the H2O molecules can be split. They can be split into a positively charged proton and a negatively charged hydroxide ion, so OH-. At any given time in a glass, even of absolutely pure water, there will be tiny quantities of H+ and OH- in our glass. The big half arrow on top here means that the equilibrium, this symbol overall is an equilibrium symbol, but the fact that the half arrow on top is so much bigger means that the equilibrium is very, very far over to the left. So it's nearly all water molecules, but not entirely. As you'll probably know, pure water is exactly pH neutral, pH 7. So there are exactly the same concentrations of H plus and OH minus. But of course, we can put other chemicals into the water which dissolve to make solutions and react with the water molecules, and these reactions can generate either more H plus, making the solution acidic overall, or OH minus, making the solution basic overall. Note the use of square brackets here at the bottom of the slide to denote concentrations. If you haven't seen this used before or forgotten, that's what the square brackets mean. So square brackets around the H plus symbol mean concentration of protons. So we've established that it's the H plus and OH minus concentrations that dictate whether a solution is acidic or basic. So why then, you might wonder, aren't these the terms that we use regularly? Why do we say pH rather than talk about proton concentration or hydroxide concentration? Well, the answer, like a lot of things in chemistry, is just convenience. You see, pH is actually an abbreviation of something. It's an abbreviation of this: minus logarithm to the base of 10 of the proton concentration of a solution. All of you are going to meet logarithms at some point in your academic journey. They're a kind of basic component of university level maths. I'm only going to tell you now what you need to know about them. They are a mathematical function for turning very big or very small numbers into more regular looking numbers to make them easier to deal with. In a glass of pure water, the concentration of protons is 1 times 10 to the minus 7, or 0.0000001 molar. If you need to learn about moles and molarities, by the way, if you need a recap of that, we are in the process of making a workshop video on that subject. But for the purposes of this video, molar is just a unit of concentration. You can see, therefore, why it's much easier to say pH 7 rather than a proton concentration of 0.0000001 molar. How would people follow that effectively? And you're much, much more likely to make a mistake just in writing the correct number of zeros. So that's why we say pH 7. Much, much easier, much more straightforward. Now, if you want to answer exam assessment questions about pHs and proton concentrations, the absolute basic skills that you need is to be able to at least convert between them. So in all of the following, note that the square brackets refer to concentration, in this case the proton concentration. So first, to get a pH value from a given proton concentration, on your calculators you need to type minus, then you need to type the log 10 key. Your calculator may then open up a set of brackets automatically for you to enter the proton concentration in units of moles per litre or molar, or you might have to do it yourself. And then after you've typed the proton concentration, close your bracket and press equals, and that should do the trick. To get a proton concentration from a pH value, you need to find your 10 to the power of key. Just highlight it here. 10 to the power of. In the case of this calculator, it's actually the same key as your log to the base 10 key. You just have to press shift to activate it, but obviously not all calculators are the same. But anyway, you press your 10 to the power of key, and then you press minus, and then you input the pH value. Again, you may have to put in a set of brackets yourself, or your calculator may insert the first bracket for you. and that's how we convert pH value to proton concentration. Right, have a go at these 2 quick practice questions to make on your own calculator to make sure you've got the techniques right and can follow the steps on your own calculator. Any problems with basic calculator functions and things of this nature, you need to see the University Academic Skills Department. They have specialist maths advisors who will be able to help you. There's a link at the bottom of the slide. So have a go at those those simple practice problems now. Pause the video, and when you've got your answers down, unpause it and I'll reveal what the correct answers are. Okay, here they are. They're what you should have got on your calculator or on Excel. If you used Excel, bear in mind that if you have on-campus exams, you are going to have to use a scientific calculator for those. Obviously, you won't have Excel. Right, let's move on. The pH scale for measuring how acidic or basic a solution is usually pictured running from 0 to 14. Although pH can be even lower or even higher than those limits. You can see a nice pH scale here with some indicators as to where common household and biological substances kind of sit on the scale. It's important to understand that every time we change the pH scale by 1 unit, we are changing the proton concentration in the substance by an order of 10. For example, this strong acid here at pH 0 has a proton concentration of 1 molar. But the stomach acid, which sits at the next pH unit up, at pH 1, has a proton concentration of just 0.1 molar, so it's 10 times less. If you want convincing of this, you can check the relationships using the simple equations that we met in the previous slide. Now we measure the pH of a solution using a proton selective electrode, commonly just called a pH probe, which is sensitive to protons and to no other chemical species. The presence of protons in the solution that the probe comes into contact with causes an electric potential to form, and this can be measured by a device called a conductivity meter. So in this picture here, this is the probe part of it, and here it's attached to the conductivity meter, which gives the reading. The electric potential that is generated is dependent on the concentration of protons in solution. You'll probably recall from previous education that when we add a base to an acid, the hydroxide ions present in the base neutralize the protons in the acid to form neutral water molecules, as you can see in this chemical equation up here. Then as we add more base, there becomes an excess of OH minus in the solution, and the pH shifts to an alkaline pH, above 7 in other words. We can monitor this reaction by a simple experiment known as a titration, which many of you might actually have done in labs already. All the titration basically means is that we slowly add base to acid in a controlled way, perhaps in increments of 1 milliliter or 0.1 milliliter, and we monitor the pH of the solution using our probe. Now when you titrate a strong acid like hydrochloric acid against a strong base, this is almost always sodium hydroxide, the data that you get looks like what we see on the left. So on the x-axis going along the bottom, we've got volume of base added or moles of base added, doesn't really matter. And on the y-axis we've got solution pH. It's called a titration curve for obvious reasons. Now what's very important to understand is that the way that the hydroxide ions react with the protons doesn't change as we start to increase the pH. One hydroxide ion always reacts with 1 proton. That doesn't change. In fact, if we were to plot instead proton concentration against volume of base added, you'd pretty much see a straight line gradient as shown on the right. The reason for the shape of the graph on the left is because of the logarithmic relationship between pH and proton concentration. For example, at the start of the titration curve, down here where the blue arrow is, the proton concentration in solution is absolutely huge compared to the number of moles of base that are added with each increment. Whereas here, at what we call the inflection point, where the gradient becomes steepest, the proton concentration has decreased exponentially from here to here. And so because of that, the number of moles of base added with each increment becomes very significant compared to the overall proton concentration. You can think of it as almost as if somebody steals 5 gold coins out of a treasure chest containing millions of gold coins. Nobody's going to notice that. Whereas if they steal 5 gold coins from a pile of 10 coins, it would be immediately noticed. I've gone into some detail on this because it is important when we come back to talk about pKas. Speaking of which, let's move on to talking about just that. Right, to understand pKas, we need to talk first about the difference between strong and weak acids. Now, the typical strong acids of the type that you may have seen in labs already, they exhibit a type of behavior called dissociation. They dissociate completely when added to water. Using hydrochloric acid, HCl as an example, this means that the HCl molecules all split apart. They all split apart into protons and chloride anions. If you were to add 1 mole of pure HCl to some water, it would dissociate into exactly 1 mole of protons and 1 mole of chloride anions. This is the mark of behavior of a strong acid. Weak acids, on the other hand, include various biological buffers, for example, hemoglobin, and importantly, many drug molecules. Now, when you dissolve these species in water, they do not fully dissociate into protons and anions. Rather, they partially dissociate, and they reach what's known as an equilibrium between the dissociated and associated forms. Equilibrium is a really important term in chemical reactions, and it basically means the point in a chemical reaction where the rate of forward reaction equals the rate of the backward reaction, making for a steady state overall. We're working on a video all about acids and bases as we speak, and this will help reinforce your understanding here when it's finished. The extent of dissociation of a weak acid varies significantly depending on which weak acid we're dealing with, because there are different levels of weakness. Some acids are weaker than others. Now, the term which describes the extent of dissociation is called Ka, with a capital K and a lowercase subscript a. It's called the acid dissociation constant, Ka. We can calculate the value of Ka for any weak acid using the equation shown right at the top. This is probably the most important equation to be able to use when talking about acids and bases and solving calculations problems. It's called the Henderson-Hasselbalch equation. The terms you'll recognize from the previous slide. Hopefully, you can see that the more a weak acid dissociates into protons and anions, the larger the value for Ka is, because the numerator terms become bigger and the denominator therefore must get smaller. So big Ka values equal stronger acids. Smaller Ka values equals weaker acids. Generally, in the modules you're taking and the types of chemicals you're going to be asked questions on, the Ka values that you're going to come across are going to be very small. For example, the Ka value for paracetamol is 3.2 times 10 to the minus 10. I'm not even going to attempt to read out the correct number of zeros. There we go, I've written them on the slide there. So perhaps you can see where this is going with respect to pKas when we're talking about very small numbers that need to be represented simply. As you might have suspected, the relationship between pKa and Ka is exactly the same as the relationship between pH and proton concentration, and you can convert mathematically between the two in exactly the same way. So the pKa is simply a convenient way of expressing the acid dissociation constant without having to write very, very small numbers. Exactly the same concept as pH. So that's one important relationship. Another very important relationship is as follows. This is between the pH of solution and the pKa of a weak acid. When pH of solution is equal to pKa of acid, the ratio between the associated and dissociated forms of the acid is exactly 1:1. There are equal quantities of the associated form and the dissociated form, the protonated form and the deprotonated form. So when the pH of the solution is below the relevant pKa of a given molecule, that molecule is going to be mainly associated or protonated. When the pH is above the pKa, it will be mainly dissociated or deprotonated. This is a really important concept and often forms the basis of exam questions. So make sure you are clear in your head about all of these relationships. Now, just to complicate things a little bit more, there are two distinct types of functional groups that we need to be aware of. If you don't know what I mean by functional groups, watch our series of videos on organic chemistry, which will explain what they are and their significance. Now, one thing that those videos won't go into is that many functional groups have the ability to act as weak acids or bases. In other words, depending on the solution pH, those functional groups can associate or dissociate with a proton, as shown in some of these in the examples at the bottom. And this, as I've said before, is also called protonation and deprotonation, gaining a proton and losing a proton. It is quite easy to differentiate between acidic and basic functional groups. Acidic functional groups have a pKa below 7, whereas basic functional groups have a pKa above 7. Acidic functional groups that you're likely to meet on your travels are carboxylic acids, but also sulfur-containing functional groups. The basic functional groups you meet will be mainly amines and amides. These I would say are the four big ones to watch out for in life sciences degrees. Another thing that's important is to appreciate the difference between protonation of a functional group and ionization of a functional group. Now, when a group is ionized, it becomes positively or negatively charged rather than neutral. It's very much the same concept as a neutral single atom becoming ionized. The same thing can happen to functional groups in organic chemistry. And the nature of the functional group dictates whether it's going to become a positively charged cationic functional group or a negatively charged anionic group. Oxygens and sulfur atoms are very, very happy, energetically favourable for them to be negatively charged. Whereas on the other hand, nitrogens and phosphoruses as well, they're quite content with being positively charged. You'll very seldom see it the other way around. So let's look at this carboxylic acid and this amine as an example. You can see that below the relevant pKa's of the functional groups, both the carboxylic acid and the basic amine are associated with their extra proton, and therefore they are protonated. However, you can see that the acid is unionized, not charged, but the amine is ionized, positively charged. Above the pKas, you can see that now the acid and amine are both dissociated from the extra proton, therefore they are deprotonated. However, it's now the opposite way around. The acid is now ionized, carrying a negative charge, and the amine is unionized. Why it's important to know and remember this is because, in general terms, an ionized drug molecule prefers to stay in aqueous or watery areas of the body, in plain English. It is termed hydrophilic, water-loving. An unionized drug molecule is less happy hanging out in aqueous areas of the body, and it can pass through phospholipid cell membranes. Because it interacts a lot more favourably with the fatty acid tails, it is more lipophilic, fat-loving, and hydrophobic, water-hating. And this is all very, very influential to the rate of adsorption of any drug molecule through the gastrointestinal tract. So again, this is quite fundamental. You even get some molecules, this is the most complicated thing we'll look at, you get some molecules which have both acidic and basic functional groups. So both sets of behaviours that we saw 2 slides ago can be exhibited. Have a go at this practice question to see if you can get your head around this concept. So pause the video now, attempt the question, and resume when you're ready. So here's the answer. It requires a bit of thought, this. Firstly, you have to identify which group corresponds to which pKa. Now, we know, because I've told you, that carboxylic acids will be expected to have a pKa below 7. So that must represent this pKa of 2.34. And therefore the amine, which is the basic group, must be pKa 9.6. The solution, we're told, is pH 7, which is far above the acid pKa. So this group is going to be mainly deprotonated, and it's going to be ionized. However, it is quite far below, 7 is quite far below 9.6. So the amine group is going to be protonated and also ionized. So the dominant form of the molecule will be what I've drawn here, simultaneously positively and negatively charged. That does happen. It does happen in biology and in nature. You get molecules which have a positively charged end and a negatively charged end. They're called zwitterionic molecules. The next concept that it's useful to get your head around is the behaviour of weak acids and bases in titrations, and what this behaviour actually looks like on a titration curve. Let's imagine again that we're titrating some common lab acid like HCl against NaOH, sodium hydroxide. But this time there's something different. This time we've got a weak organic acid dissolved in the HCl. The titration data you get is going to look something like this. And the explanation is as follows. Now, initially at this first point, point 1, the pH of the solution is obviously way, way below the pKa of the weak acid. So the molecule just stays completely protonated. And all that happens with the hydroxide that's added is it just reacts with the strong acid as normal. However, as the pH of the solution starts to approach the relevant pKa at point 2 here, the weak acid molecule will start reacting. The weak acid molecules, rather, they will start reacting. They will start giving up their protons to react with the added hydroxide. The weak acid molecule will work to try and retain the pH of the solution around its pKa, which is where it's happiest. And this causes this funny bump on the titration curve. But eventually, when you add enough base, all of the weak acid is converted to its deprotonated form at 0.3, and then the base continues to react with the remainder of the strong acid in the solution. And then beyond pH 7 at 0.4, there's again an excess of base in the system, and the rest of the titration curve looks fairly normal. It's important to understand that the overall shape of this titration curve is dictated by the interaction between the strong acid and the strong base. The interaction between the weak acid and the base is what gives these mini inflection points here, superimposed onto the main curve. And actually, with the help of quite a complex equation, you can use data like this to accurately calculate the pKa of a weak acid or a weak base that is unknown. But you will not be asked to do that in your undergraduate degrees. That's just for information. Final important concept. An important biological function of some weak acids and bases is to act as what we call buffer solutions. The word buffer, as we see, means different things to different people. However, in a chemistry context, a buffer solution is one that contains a chemical species that will react with any free H plus or OH minus introduced to the solution to maintain pH at close to a constant value. Always remember, as I said before, that weak acids and bases want, in quotation marks, the pH of the solution to be maintained at more or less the same as their pKa, and therefore they will work to try and maintain this. So if excess protons are added to the system where there's a buffer chemical in the solution, the molecule, as we see here, will associate with them to remove them from solution like this. If excess hydroxide, on the other hand, is added to the system, the molecule, the buffer molecule, will dissociate with some of its protons, so they can in turn react with the hydroxide to form neutral water, so that again the overall pH of the solution is unaffected. There is an equation that you can use to precisely calculate the pH of a given buffer solution, provided that you know the pKa of the weak acid or weak base and its concentration. However, we won't go into that equation in this video. This is much more about basic theory. And in fact, as you may be relieved to hear, that's the end of the learning material. So I'll just leave you with a recap of the learning objectives. Congratulations if you made it all the way through. This was probably our toughest and most complex video. As always, there are plenty of practice problems to have a go at to make sure that you've understood the learning. If you're watching the video when it was first released, please come along to the workshop session to practice and get extra help from one of the tutors if necessary. If you're watching this after the workshops are finished, in a revision period, you can access copies of the practice questions and answers using the links provided underneath the relevant video. Thank you for watching.